Okay, good afternoon, everyone. So welcome to the afternoon session today. Okay, so I hope that we won't take so much time for me to explain what you're going to do and what we are going to expect in this hands-on. Okay, so before I start the session, can I ask how many of you do have experience in Linux, and how many of you don't have any experience in Linux or in doing in terminal, what do you call it, programming? You can put in the chat or you can raise your hand. Okay, so first, who don't have any experience in Linux? One, three, okay. So quite a number, yeah. Four, you can see, and also there is a chat here, ada another two. Okay, so 1, 2, 3, 4, 5. So I assume all of you use Windows, what we call it, computer or laptop, right? So you might have a limited experience in using Linux. So never mind. I hope that the tutor after this, you are going to the breakout room, and then the tutor will help you in understanding of how we're going to run the code, and also to learn how to do the evolution of the Stella model. So my focus is we are going to do for one solar mesh first, right? And then if any of you would like to explore more, you are welcome to. But first of all, let us start to see that introduction of Mesa code, and also how we are going to explore it more. Maybe you can do for your final year project, your graduate study, and so on. Okay, so hold on. Okay, so the one that I introduced to you, the necessary English code, is a code that is, like I mentioned in the lecture this morning, is an open source code. So you can freely download it to your Linux machine or in your Mac, but it does not support Windows. And like I mentioned before, this is a 1D celebration code, right? So if you go to the Mesa page, they will give you some guideline how to install and what are the prerequisites that you need. I guess that the organizer already installed the Mesa code in the ITB HPC, another one is in Brim. Okay, so I hope that everyone can access it, or for those who already have your own, I should give a try. Okay, so when you want to install this Mesa, there is two ways, right? So either you can install it directly, download from the page, or if you have a remote computer, you can download it from your remote computer that have Linux. Okay, so I'm not going to go to detail, just going to show you what are these things, and then you can have a look later on after finish the class, and this is the requirement that we need, and you can install Mesa by the given instruction. Okay, so when we want to run cell evolution code or install Mesa itself, the knowledge of how to set up the system is crucial. So that's why you can see that many people who are doing astrophysics or astronomy good in computer, because once we install the code, we need to set up the environment for your computer. If not, the code cannot connect to the compiler. Okay, so you need to set up the installer for Fortran, for numerical differences, NDIF, and also you have to install pgplot if possible. So unfortunately, my laptop now is not support with a pgplot because I'm using a Mac, since the M1 does not support pgplot anymore. So, and I'm going to show you just plotting by using Python after this. All right, so I already download the Mesa. Yeah, hold on. I share my terminal. Okay, so when I talk about terminal, so this is in a Linux environment or in a Mac, we have what we call as a terminal. Terminal is where we can communicate with the computer directly to the system. Okay, so it is not click and play. So we have to use terminal to communicate with the system of your computer, right? So I already installed Mesa version 22051. This is the latest version. And from here, we can see that what are actually contained in the code. Okay, so I just give you some briefing here. So like I mentioned in the lecture, we are solving the 4 different equation with the input physics and everything. So when you, if you're able to see the Mesa code, if you are installed or you can see in the HPC later on, you find that there is a lot of folder in Mesa code. It means that when you want to put the input physics, for example, your, what they call it, your atomic value, your nuclear reaction rate, your opacity table, what else? Your chemical abundances, your atmosphere, everything. That come with their own, we have to write our own code to as an input for the solution of our stellar evolution code. So that's why you can see that if you, for example, I open one of the folder here, I choose chemical. So chemical here is to explain the what the nuclear reaction. So you go to a private or a public folder, and then we can see there is F90, means that there is a Fortran 90 or 95, depending on what are the nature of the code. So when you open it, this is the Fortran code. This is one of the subroutine of 100 subroutine that embedded in the Mesa stellar evolution code. So this is written in Fortran. So from here, you see that how it define the, what we call it, the physics of the cell evolution, what are the integer, the parameter. So it's not just simply we solve for the equation and that's it. No, it doesn't work that way. So that's why you can see that this is a very massive code, has been contributed by a large group in order to build this kind of code. So here is all the, for example, chemical composition that produced in the star, and we have to define what is the isomer, the abundances, and so on, right? So this is, I just show you the example. So if student want to do what we call it research afterward, you have to identify what a problem that you tackle, and then you can add it to the certain, what they call it, folder, the subroutine that you want to tackle, and then you have to recompile back again before you can use the code. Okay, so that is another major thing for the future work. For example, if you're interested to do in the stellar evolution. All right, so I'm going to show you in the Mesa code. One good thing is anyone can learn how to learn Mesa without, if you don't really know what is the background, but at least you know what is how the idea does it works. And also after that, you are going to understand how to run the code by using the input physics that I explained earlier in the lecture this morning. Okay, so the example is located in the star data. Sorry, in the sorry, let me see. Oh, not star, in star, I think. Okay, so in star, this is what we call it the where the, what they call the sample of the code, and also the major compilation of the code running. Okay, so then if you go to, for example, your test suite, okay, so here you will see that there is a lot of folder inside the test suite that can be used to test for any type of star that you want to test. So here, what does it mean? It means that this is 1.3 solar mass with high metricity, 1.4 with I think main sequence with I don't know what is the mono ni. Maybe you have to read in the readme. And then 1.5 with diffusion. It means that we have atomic diffusion in this one solar mass star. This is massive star, 12 solar mass star from pre-main sequence to the core collapse, which is it can calculate just before it collapses, and so many more. Okay, so we have some variety of what they call it example, but this example is not run yet. It means that it just gives you some initial file, initial condition that you can test to run. In order for you to run, you have to copy this folder. For example, the hands-on I'm going to show it to you is the one pre-main sequence white dwarf. So when you want to run this thing, you have to copy and put it outside the Mesa code itself. So that is how it's been done. So when you take the example, take it off from the Mesa code, and then you can put anywhere in your computer, and then we are going to run it here. So how that your model's going to recognize the code, we have to assign a directory in the folder that we want to run the models, and then it will call the code from there. Okay, so when it call from there, and then you can easily run it anywhere, doesn't matter. Okay, so in a Linux, it called copy -r. This is to copy a folder. So I move to another directory that I created, which is called models. Okay, so I have models here. Okay, so I want to rename as something else for this code. Hold on, I'm going to stop the calculation first. I have tested it before, so I just want to make another copy. Hold on, I want to start from the beginning. Okay, so I copy the fresh one into the directory of models. Okay, so now I'm going to the model directory. So that this one means that you're going up to upper directory. Okay, so from here, I have this one copied directly from the Mesa test suite. Okay, so you can see here, I have several models here where I tested before. And from here, we are going to do some hands-on after this. I think the tutor will assign you into groups to do the what they call it, exercise together. And I expect you to produce some kind of short, what they call it, report, maybe 1 or 2 pages, what they have learned or what you understand in running the code. Okay. So from here, we can go to the, what they call it, this is where we are going to start our models. You can see here we have several, what they call in list. So in list here is what we call as our input file. So input file for us to edit or also to assign what are the input physics or the one that we want to set. For example, the mass, we want to set the time scale, we want to set the number of model we're going to calculate, and also if you want to set nuclear burning, rotation or no rotation. So this is technically the one that you see in the Mesa web, but now is in terms of the file. Okay, so README is just some README files. CK, I think this is for to clean the calculation. History column list is if you want to add more info in your column, you can edit the column list, and then you can see that here we have to make. So it means that when you want to run this code, you have to compile it first. Okay, and then they have several what they call it command here. The make, rn, everything is just for you to recompile and compile the code. Okay, so you might ask, why we have a lot of in-list file here? Okay, so Mesa is quite a unique code compared to other codes that I have used before, because what it do is it will run the code by stages. What does it mean? So it means that first you run this one, you can run from the prism. It means that before time 0. Okay, so this is where the what they call molecular clouds start to attract each other and form what they call it, some molecular gas before the hydrogen start to burn at the center. Okay, so we have several in-list file, and then we have in-list header. So in-list file here is, for example, the first one is where you want to start the what they call pre-main sequence, and after that it will move to, if I'm not mistaken, the helium core burn. Okay, So you helium, I think, or AGB, I don't remember, but this one is like a sequence, yeah. So when it's a sequence, it go to a pre-main sequence, it go to main sequence, it goes to the core of hydrogen burning, and then it start to do the helium core flash. This is the 3 alpha, what they call it, burning, and after that it will go to the white dwarf. WD is white dwarf. Okay, so there is a helium flash burning. So how we want to start this? Okay, so I'm going to show you step by step. So first, we have to check what is our in-list header. So in-list header is the file where it will call where is the MESA code is. Okay, so I open the in-list header. So when you start open in-list header, they will have something like this, MESA directory blank. So this one is actually you have to give the directory where is your MESA located. Okay, so in my case, okay, so let me show you my screen. So this is my MESA. So I type PWD. So my MESA is located in my user Norhasliza document research MESA. This is where is my MESA code located. So I have to copy this and I have to put everything. I have to call the MESA. I think if you do in the remote machine, this one can be skipped. But since I doing locally in my computer, I cannot do automatic. Yeah? So it depends on how your tutor will tackle for this one. But if you want to do it by your own at home, so this is how you do it. And then you save it. And I have to do it for the rest of the file. Just bear with me for a while. Everything that with header, you can see that everything that with a MESA directory here. So you can really rename everything and make sure that the code can call what is your in-list for. Okay, so after that, I'm going to show you how we edit the input of the parameter for this particular thing. Okay, so we have a core of hydrogen burn. Okay, so the core of hydrogen burn is your actually your pre-main sequence. Since everything is already in my buffer, so you can just when you copy paste, it should be already in your buffer. You just paste it as is it. Okay, so and then you can run the core burn, and then we have helium burn header. It may take some time to do this, but don't worry. So this is to reduce the crash in the code later on. Yeah? So if you don't do this, it will crash, and eventually you have to redo everything. You have to restart back again, which is a bit tedious. Yeah. Okay, so we have one more, which is the 2WD header. Okay, so I think that later on your tutor, I think some of them already have experience in running MESA, should able to help you in dealing all this, what they call it, things in MESA. Okay, so now we have already, I cleared it so that you can see it. You can see more what from the clean page. Okay, so from here you can see that what is the first thing that we have to set for our input. So here they already have some default, so you can open the in-list start. Okay, so you can use any other, what they call it, editor if you want, no problem. So this is, I just use my Vim editor to open the file and edit. So you can see here, the start job is where the compilation or calculation will start. Okay, so from here, they already set some compilation of the false. So it means that the log file, when we run it on, you see that when we run the file, they don't show everything. They just show you what are the things that we want to set. So in this case, and after that, we create pre-main sequence model. So if you want to run from ZAM means that 0 each main sequence, you replace true become false. Okay. So after that, it will start exactly from ZAM. This one we create pre-ZAM, pre-main sequence. Okay. So, and after that, we want to save each model when we terminate. If you put false, when they terminate, the model won't be saved. Okay. So it depends on what is the storage of your computer. If you have large storage and you want to save everything, you put it as true. Okay. And after that, what is the best thing when we want to save the models? The true. So when your models crash or stop because of the correction of numerical correction or whatever, we can restart at that particular models. So this is what the usage of this one. Because sometimes we are going to calculate, for example, your file become from 1 until 1000 file. So we don't want to restart our calculation from 0, right? So we want to stop, probably it stop like 500 models. So we want to furthermore, so we can start exactly for 500 that being saved as a start mode here. Okay, so from here, this is optional. If you want to terminate your, what they call it, code, you can put the log at lower limit. It means that if the L is very small, it can terminate the code. Okay, so here is the equation of state of if you want to put, for example, you want to test for neutron star or whatever, we can add the new equation of state if you like at this part. So here the slash exclamation mark means that the code is being commented. So they won't read it. It's just that we uncomment the code. Okay, and then we have opacity kappa. So the base or the metricity of our code or our model is 0.02. This is taken from the Griffiths and Sauval 98. Later on, you might ask, what is this? What does it mean by Griffiths and Sauval? Griffiths and Sauval is a compilation of abundance that have how we want to determine the initial composition. Okay, so they have GS98, we have S+09, and so on. Okay, so from here we have what we call it several abundance. But if you choose different, what they call it, abundance from different author, this Z base need to be calibrated. I don't put in detail here, but this is more like if you want to do some research level work. So it means that 0.02 for Griffiths and Sauval 98 might not be the same with S+09. Okay, so because of the how they estimate the atomic what they call it molecular weight for that particular metallicity. Okay, so from here we are going to use a type 2 opacity of true. So this is just either we want to see the opacity is okay or not. If you want to make some different way, you can edit anything. So this is editable. So you can edit, for example, if you want to test for lower metricity, you can test become 0.01, 0.0 something. It depends on what are the preference of your metricity. So here we are going to test metricity, which is producing our sun, our current sun. Okay, so here is just the control. So here if the lower limit is 1, it means that we are going to get our log L is 1. This is for the sun because the what we call it, the soil luminosity is 1. So we put limit as 1. And then the maximum number that will be produced for the models is around 1000 per run. Okay, so you can what they call it, you can make it more or you can make it less, depending again how much your computer can handle it. So for example, if you have a high performance computer that have storage like a few terabytes, you can add more, no problem. Okay, so here the limit is 1000 just to run in the normal computer. And then here is our mass for our star, which is we are going to run for our sun, which is 1 solar mass. This is also editable. You can change to 2 or 3, whatever. And this initial Z also correspond to the Z base that we set earlier here. Okay, so it means that, so you might ask, what is the value of what they call it, hydrogen helium? Okay, so there are two ways. Yeah, so from here you can also add initial H, for example 0.7, or you can add initial helium-4, 0.25, for example. Okay, because how we want to determine the composition? Composition is just that X plus Y plus Z equivalent to 1. Okay, so that is how we determine the composition. Okay, so the this variation control target is just that how many mesh point or the time step that we require when we want to calculate. This is the position is around around -3, 0.03, the position of each mesh point being moved. Okay, so photo interval is okay. So photo and profile is the one that for the structure. Okay, so for each structure we have 100. For each 100 models, it will save your profile. Okay, so the next one will be 200 and so on. So if you want to have more precise structure, you can edit this one. This one become what we call it 50 or 10 or whatever. So if you make it smaller, it means that the code will run much longer. Okay, so it will take much time because it's going to read and save the data. The data will be a lot. And this is the history interval is for evolution. So for each 10 model, it will save in the history. And terminal interval, when we run later on, you will see that it will show you the interval of what are the output we are going to calculate. So this is the header frequency 10, correspond to the history and also terminal interval. And this one, if you want to make it smaller, like I mentioned to you, you can put it 1, no problem. As long as you have a larger space, you can, what they call it, calculate. So I have no idea about MESA, but the normal stellar evolution code that I calculated, one model will eventually take around at least 1 gig. Depends on precision of how we want to very if you want to have a final mesh, it means that it will take quite large of what they call it, the space. I think for Sun it will take maybe like few megabyte only, so it's still safe. So that's why I choose one solar mesh, so you don't have to worry about space. So it will still save in this sense. Okay, so debugging is if you have, for example, when you calculate for new physics, for example, or if you calculate new input, sometimes the solver cannot solve. For example, Rajputa or the relaxation method unable to solve. So it will give some report when the program crash. It will say that it will crash because of what. Okay, so it will reason out. It's either for the solver, the error, or if there is some bad numbering. For example, when it's calculated, might be infinity somehow when you update the result, or probably there is not a number. None is not a number, especially when we iterate, when we solve the matrix, everything. This might be what they call appear in our result later on. Okay, so these are the debugging tests. Usually this one is done by the developer, especially people who do the still evolution code itself. If you are just a user, you don't have to worry about that. If you are developing the code, these are the tests that we are going to do to see that at which part it produce the error. Okay, so here is all the solver, or if you want to add at certain time, if you want to stop, you can add also at this this part. Okay, so let me see what are the other things. Okay, so that's it. So this is for the starting point. So you can see that here we have several also in list. For example, I just go to the main sequence, to the and for hydrogen burn, for example. Okay, so here is where after it start a pre-main sequence, it start to what they call it, save the models and calculate back again for the pre-main sequence. And you can see that some of the value we have to put some limit. For example, the hydrogen burn is start when the content of hydrogen being burned around 1%, or in this case is 0.01%. Okay, so this one where we're going to see that okay, the hydrogen is start to burn, and we also have to tell the computer that when the hydrogen, what they call it, has been exhausted at the core, they have to move to the helium burning phase. Okay, so this is being done by all the English file, and how we want to determine either we want to have a mixing, we want to have factor. This is factor is for the one solar mass. Okay, so and either, and here is where the stellar winds come. So here they choose already around Raimond and Blocker for RGB and also for the AGB star. Okay, and after that, the scaling is, don't have to worry. You can see that when we move to main sequence, the interval become is changed a bit, because we want to see that this is where the crucial part of the, what they call it, star evolve. So usually for sun, we only run until end of a hydrogen burning core. So if you want to run until white dwarf, you can have a look at, I want you to explore to see all this in list, and then to try to understand by using the MESA web. The explanation, you can test and you can run the code. Okay, so then how we going to run the code? So before we run the code, we have to compile. Okay, so let me check the make file first. If it require directory, yes, it require a directory. So we have to put another directory here. Okay, so it's the directory where we are going to compile our code here. Okay, so I move on to one more. Yes. Okay, so then let me compile all the input that we have. We can see here there is no error, everything being compiled correctly, and all library that needed is being linked. Okay, so then we can start our run the code. Okay, so run the code is, we are going to use RN. Okay, so before I run the RN, again, let me see, they require some directory here. I put the directory where is the location. Okay, so this is, we start to run the code. Okay, I click so that you can see it from here. So I calculate RN, and you can see now we are starting to calculate the cell evolution. You can see that this is all the log file that we are going to observe. You can see that now it start the calculation, and it start to call the nuclear input. You can see that here it called the nuclear data rates and start the pre-main sequence. So all the data is being calculated real time. If you still remember in the lecture, I put some what they call graph to video. Actually, you can turn it on if you install pgplot. Here, I don't install pgplot, so we cannot see the interactive plot in the real time. So from here, you can see that all the step size output being produced for each 15 or 100 models. Okay, so it calculate everything. And after that, you can observe your result when the code is crashed. So technically, this one will take around 2 hours to what they call it, to complete by using the M1 or what they call it laptop. I think if you have HPC access, it will be maybe around half an hour it will complete it. This is what I experienced if you have a very powerful HPC. So it should be very fast to calculate. If you calculate in the local computer, it will take slower. Okay, so from here, I'm going to show you how the input look like. Let me share back again. It paused at one point. Okay, so I'm going to show you the how this input look like. Okay, so I'm going to my models, the one that I calculated before. Okay, so the result will be in the log file. If you go to your log file, CD log file, you see that there is a history. Let me put it up here. Okay, so here we have history data. This is evolutionary data, I mean that from pre-ZAM until whatever that I stopped the calculation just now. And then profile mean the structure, the onion layer. So each onion layer, so for each one time there is one onion layer, depending on how many models that you save. Okay, so from here I have around let me see, 16, 23 data, 23 profile for each one. So we can have a look for the evolution first. Okay, so this is how the evolution data look like. So you can see that for each number, that's why it don't start from 1 because we already put starting from 100 just now. So that's why after that it start each 10. So because why? From 1 until 295 is the pre-sum models here. So that's why it don't save there. And after that, we are going to see that we have for each model, we have the age, we have the time difference, the mass, the what they call it, this is the mass loss, this is the rate of the mass loss, and also all the value. You can have a look after this. Yeah, so there is we can have our protoproton chain, our EP chain, and so on. Okay, so this is for our profile. So history, the structure. So we can have a look for our profile, which is 23 data. Okay, so this is structure. Just now is evolved from 0 to whatever time, and this is for the particular structure. So structure and profile are two different. I mean, from the structure, it being compiled to the evolution, right? So from there we have another for each structure from center. This is from center to the surface. Yeah, center of surface. You have all the data that being calculated until whatever layer. Here we have, I think, 1,000 plus layer. Okay, so from here we have quite a large value, and then you can see that either your profile will follow the standard result that we require. Okay, so right, at this point, I think I'm going to stop here. You can plot your data and see that how it looks like. There are two ways to see either your data is okay or not by calculating this. Where one thing I already give some plot. The plot there is independent. You don't have to have special, what we call it, link or something like that because that is I wrote by my own. Another one is you can use Mesa Reader. So if you want to use Mesa Reader, you have to install the Mesa Reader, Pi Mesa Reader master here. Okay, so here I already download also from the same websites. And then after that, you have to run, I just show you how it looks like. And then you have to run Python setup.py install, and it will install the system for you. Okay, so that is one of the Mesa Reader. And how to use Mesa Reader. So I already, what they call it, create a simple code to read the Mesa Reader. So how to read the Mesa Reader, let us have a look first. Then after that, you can go to your own, what you call, hands-on and do it by self. Okay, so here to call, if you know Python, oops, sorry. If you use experience in Python, so in order for us to call Mesa Reader is you have to import Mesa Reader as MR. This is similar like if you want to import map.lib, you want to import numpy, pandas, and so on. Yeah. So this is how we have to import. This is the parameter that I set up myself. This one is not coming from Mesa. This is coming from Python. I set up so that we can have a nice plot routine so that this is suitable for publication, for example. And after that, we have to update all the parameter that we set here. Okay, so here, then we have already import Mesa Reader as MR. So we assign H as some variable as a Mesa data, and then we have to load the data. So here I want to plot the evolution data. So I have to give the directory where is the location of your data. So it means that you can put this one at anywhere, and then you can plot what we call it, the the result here. Okay, so from here we have to see that what is age and everything. This one is correspond to the header. Okay, let me show you what does it mean. I hope that, let me share the whole desktop so that it's easy when I want to move from one to another. Okay. Okay, so I go to the PD log file. Okay, so for example, we have the history. So you can see here, what I did is we have to assign, for example, if you want to see the start age, so that you have to assign exactly the name as the header in the history. Okay, so here I already put several. You can add more if you want, no problem. This is just that I do it quickly. And after that, I plot some, what they call it, a result from the temperature density, the HI diagram, the evolution of mass and age, and also some abundances. Okay, so this is quite easy to do. And then you can just run it by calling Python history plot. It will take some time because I put some parameter there, no problem. Okay, so this is the one that I already calculated before. So from here, we can see it's a central density with temperature, the T0C diagram. This is the, what we call it, HI diagram. And this is evolution of mass with years. And also this is for the hydrogen with years. Okay, so this is the time evolution. Okay, so you can give a try and test it. So I also have another plot, the one that I give it to you in the Google Drive. So here, this is the one that I wrote myself last night. Okay, so here I use Panda instead of Mesa Reader. Okay, so I read the pandas, and then I import the matplotlib to read the file again. And after that, I just use a Panda and read the CSV and read the file. This is I'm taking from the Mesa web. Also, you can use the evolution, no problem. It's just that you have to give the proper directory. And if we want to skip header, in Mesa Reader is already set to skip the header. But if you use Panda, you have to do it manually. You have to skip how many rows, and then you have to assign how the separation column will be. Okay, so from here, again, the header is being read just similar. And after that, you just plot similar that I plot just now. Okay, so we give a try, and it should give you the same, about the same result if you plot the same thing. Okay, so this is this is stop exactly at the edge of the sun. Okay, so the one that I showed you just now is more advanced stages. Yeah. So here, if I plot the same file, it will give the same thing, but all the command are the same. It's just the file input file is different, right? So you can give a try. This is also, I have the keyboard and also the structure. The structure is the profile. You can have a look at the code and try to run your own. I don't do in Jupyter Notebook because it complains of how we want to read the column. So I don't know why. Maybe someone can fix it later on. But here I just use a native Python. And this is for structure exactly at 4.6 billion years for that sun. And you can see the profile is meshed with the standard solar model that we need. Okay, so any questions so far? I stop my briefing here. It's almost 1 hour, so I give briefing. If there is none, I think all of you can move to your, what they call, breakout room, and then start to work on from the example that I give just now. Okay, thank you to organizer. Maybe the student can start to work. And you have another, in the second half is, I'm not going to give any explanation anymore. So that is, you try to work together and discuss with your tutor to do the problem. Okay. Okay, back to you, organizer, whoever at the moment. I think it's time for you to join your breakout room. Okay. Thank you, everyone.
That's involved. So
At which step are you now?
I'm right now I'm trying to install the SDK. And
Oh,
then,
I see. So Mesa SDK.
yeah,
Right.
and then after that, I'm gonna have to. I've already downloaded both the files for the SDK and also the Mesa itself. The installing portion is kind of icky. Just trying
Okay.
to make it
Yeah.
as easy as possible for myself. So yeah.
All right. And what operating system are you using? Two of you will choose running the Mesa in HPC. So I think the others will run the Mesa in HPC too. So one of you maybe can share screen how to using Mesa in HPC, and the others can follow that one person to running in their PC, their own PC. Okay. The step-by-step has been explanation from Dr. Lisa before. So I think who follow the Dr. Lisa will don't find any problem. Okay.
I can share screen, but I don't really understand the one that Dr. Lisa explained, because I was trying to install this. So
Okay. Your friend will help you.
okay, hold on. I will. See. Okay.
So anyone can tell what will you do? What's hands-on? Okay, so how's team? So should I talk now, or will you talk first?
Yes, sure.
All right. So thank you everyone for attending the hands-on session this afternoon, Indonesian time, of course. Some of you may have like the session in the morning or even in the midnight. Yeah, because one of you is from Colombia. So thank you for attending, and I hope you really enjoy the hands-on session today. I'm not sure in other groups, but I saw quite interesting interaction and quite a lot of problems that makes the session really alive. So thank you for that. And you can continue the discussion or the experiment on your own. And remember that this project might be your assignment later for the presentation at the end of the school. So please try to understand every single project as much as possible and get prepared for the presentation session. And don't forget to submit the assignment, the report for Dr. Liza's session. And I think she asked for the report to be submitted by 16th of August. So it's like five days from now. Thank you, everyone. And before we close this session, I think there will be a photo session first. Over to, I don't know, is it Ilham?
Yes.
Yep.
Okay, everyone. Please open your camera. for the last conversation in today's lecture. And for those who have not filled the attendance form, please fill now. You can fill in the chat room. bit.ly/IPC_day4_2. Okay. Once again, please open your camera. Okay. Okay, we can start from now. Let me take 3, 2, 1. Okay, once again, 3, 2, 1. Okay, just only 29%. Okay, thank you all.
Thank you. See you tomorrow.